This video abstract presents the article Analysis and Modeling of a Boost Converter with Power Processing Reduction for PV Applications, submitted for publication in the IEEE Latin America Transactions.
Photovoltaic PV systems generate DC power that must be conditioned before being delivered to different types of loads. In this application, the DC regulator plays a crucial role, as it ensures that the power coming from the PV panels is processed efficiently and adapted to the required voltage level. The proposed converter architecture reduces unnecessary power processing by enabling a partial power flow directly from the PV source to the load, while only a fraction of the total power is handled by the converter. This approach increases the overall efficiency of the system.
This work presents the converter waveforms, steady-state operating points, gain-duty cycle relation, and the expressions for current and voltage ripple.
The two operating states of the converter, corresponding to the on and off intervals of the switch, are presented, and the dynamic equations describing currents and voltages are derived. Key parameters of the converter are presented, along with the duty cycle to voltage transfer function used for stability analysis. Pole zero plots for different component values show how parameter variations affect system stability and dynamic response. Additionally, an analysis of the partial power processing in the buffer element was carried out, which directly increases the overall efficiency of the system. This analysis was performed using Volt-Ampere VA area modeling, allowing the identification of the operating regions as a function of the duty cycle, which contributes to improving the design of the converter. The experimental voltage and current measurements obtained from the boost converter are presented, validating the theoretical results. Additionally, the partial power processing in the buffer element is analyzed, confirming its contribution to improving the overall efficiency of the system. Finally, the closed-loop experimental tests are presented, along with a dynamic response under load variations. These results allow evaluating the controller's performance and verifying the converter's stability and regulation capability under varying operating conditions.
In conclusion, this research presented the analysis of a boost converter with reduced power processing, along with a design methodology and a study of partial power processing. The results obtained through simulations and experimental measurements are presented, demonstrating a 4.21% increase in the overall efficiency of the system compared to the conventional boost converter.